Okay, today we're going to talk about Chapter 6 on circuits. And I just wanted to bring up some interesting facts about electrical hazards. Um, you can consider 100 milliamps to be a lethal current dose, and that's because it causes ventricular fibrillation, meaning that it stops your heart. So it interferes with the beating of your heart at 100 milliamps. Your body can withstand larger currents of 1 amp. It doesn't stop your heart, but it does cause burns. So a current of 1 amp, it won't kill you, but it won't kill you immediately, but it could kill you later on. It's going to cause burns inside your body. And 100 milliamps of current could kill you because it messes with the currents that are going to your heart. The resistance of the human body is very high when the body's dry, 10 to the 4th to 10 to the 6th ohms. But when we're wet, we have a much lower resistance of 10 to the 3rd ohms. So that's why when you want to not be wet during an electrical storm, or you want to be not in the shower during an electrical storm, you don't want to be anywhere near electricity when we're wet, because then we can become the conduit for the current to flow. Okay, a battery. A battery provides a source of voltage or potential difference that can make charges move. So voltage provides this potential energy, and that's what causes the charges in the area to move. And the way that a chemical battery, like this one, does it is this positive electrode interacts with the sulfuric acid, and that interaction requires electrons as part of the process. And so when the process happens, this positive charge loses 2 electrons. So that makes this cathode even more positive. And then when this zinc electrode interacts with this sulfuric acid, it produces electrons. So that interaction produces electrons, making this negative terminal more negative. So that provides the charge that keeps this potential between these positive and negative charges constant. And so that can happen once. It's like a kind of a feedback loop when when there's a load and it demands more current. These electrical process, or the chemical processes will happen so that to keep the voltage constant. And you can see here we've got we can put batteries together in series. So we have the negative side of this battery is down here, the positive is up here, and it's touching the negative side of this battery and the positive here. So this is a battery model, and so the energy per unit charge delivered by a battery to a charge carrier, and this brings the charge carrier across or against the electric field, and we call this this symbol here EMF, or EMF. It's the battery's characteristic EMF, and this E thermal here is the energy that the charge loses when it's moving from the positive to the negative, or the negative to the positive plates. And for an ideal battery, we assume this E thermal is 0. So we say our potential is just the EMF of the battery, and that's a pretty good model for the batteries that we use. A little bit more about the battery model. So we like to think of the battery as there's this conveyor belt that is transporting charge from this plate over to this plate. So we're bringing positive charge over here, and we're bringing negative charge over here. So we think of it like kind of like a conveyor belt, and the chemical reactions are what provide that conveyor belt motion of the charge carriers. And so it's just another way to think about it, is that charges are being carried from one plate to the other, but it's done through this chemical process. The EMF of batteries, they connect in series, just like that last example. So this would mean the voltage or EMF of battery 1 plus the voltage of EMF of battery 2, and plus however many batteries you have. If you connect them so that the positive terminal is connected to the negative terminal of the next, and then the positive terminal of that one is connected to the negative terminal of the next one, then you'll have the batteries in series, and you can add up. So let's say I had 3 AA batteries, each one having a potential difference of 1.5 volts. Then I would have 1.5 volts plus 1.5 volts plus 1.5 volts, and my total voltage would be 4.5 volts. It's helpful to think about a circuit and a battery, and the battery or the current or the voltage that's going through these wires and how that all works. And so one neat analogy is to think of it like a roller coaster, where my roller coaster, that motor is bringing up my car all the way to the top. So that would be like going across this battery. And then as I'm going down the roller coaster, this would be a narrow or not very steep, a gentle going down. So I can see here I get to the top and then I'm gently coming down. And so this wire here doesn't have a lot of resistance. And the way I can tell that is because it's fat compared to this one. So it's easier for the charge carriers to move through it. So the potential doesn't decrease all that much as we go along here. But when we get to here, my wire is much thinner, so it's harder for the charge carriers to get through. So my resistance is higher, and my potential goes down much faster. And now if I were to open this up, like cut the battery in half and lay it flat just to see what it would look like, I would have my going up the roller coaster, right? That motor bringing me up. I get to the top, and then on my gentle ride down here, right, for my thick wire, so there's not a lot of resistance. When I get to the thin wire, right, there's a lot more resistance, and my voltage decreases a lot going through this thinner wire. So we can talk about the loop rule. If we want to think about this, my wire here has a certain resistance, and it's low. My wire here has a higher resistance, so it's high. And so these would be switched. So I would have, if I were to think about like this last example, this would have a lower resistance than this. So when I go through this one, I'm going to have a bigger drop because my resistance is higher. When I go through this one, I'm going to have a narrower drop. So you can see I've lost 7 volts across this resistor right here, and I've lost only 5 volts across this resistor here. And then this part, C to D, is here, and I'm going back up the roller coaster as I go across the battery from D to E. These are some symbols of a circuit. So since we just showed you a circuit, it's nice to know what those symbols mean. So this is the symbol for a battery. This is the negative terminal, and this is the positive terminal. So this is the flat side of a battery, and this is the side with the little square on top, or circle on top. The capacitor, this is the symbol for a capacitor. A resistor has squiggly lines. This is the wire that connects our components. A switch. So this switch here, it's open. If we were to bring this piece down here, it would be closed, but this represents a switch, and we don't actually close it. It's accepted knowledge that it can be either open or closed. And then this is these are the symbols that we use for ground, meaning 0 volts.